Hey everyone. In this video, I'm going to walk you through the top 2 discounted cash flow problems for bonds. We'll start with bonds that pay annual interest and move on to bonds that pay semi-annual interest. For each problem, I'll show you 3 ways to find the solution. First, the traditional algebraic formula. Second, the quick and easy method using a financial calculator. And third, the powerful and flexible approach using Google Sheets. My goal is for you to be an expert in net present value calculations by the end of this video. If you'd like a refresher on what these assets are or a deeper dive into the practical application of these theories, please check out my lecture on valuation fundamentals. I'll link it in the description and on the screen. If you find this video helpful, please hit the like button or leave a comment with any other topics you'd like me to cover. Let's get started. First up, we're going to solve for the price of one of the most common financial instruments, a standard annual coupon bond. You can see the problem details on the screen, but I'll read it out loud for those listening. A bond has a face value of $1,000, a coupon rate of 6% paid annually, and a maturity of 10 years. The market interest rate, also known as the yield to maturity, is 5%. What is the price of the bond? The price of the bond is just the present value of all the cash it will pay out in the future. This includes all the annual interest payments, called coupons, and the final repayment of the face value at maturity. We'll discount these future cash flows using the current market interest rate. Here are the key variables from the problem. The face value, or FV, is $1,000. The coupon payment, or PMT, is $1,000 times 6%, which equals $60 per year. The number of periods, or N, is 10 years. And the market interest rate, or I/Y, is 5%. An important tip. Since the bond's coupon rate of 6% is higher than the market rate of 5%, it's more attractive than newly issued bonds. Therefore, we should expect its price to be higher than its $1,000 face value. It will sell at a premium. The classic way to solve this is with the present value algebraic formula. We're calculating the present value of the coupon payments, which are an annuity, and adding it to the present value of the face value, which is a lump sum. The formula is expressed as the coupon payment multiplied by the present value multiple for the duration and rate of the annuity. We then add the lump sum from the future value or face value of the note to get to the bond price in today's dollars, or its current valuation. For the equation, C is the annual coupon payment of $60. R is the market interest rate, written as 0.05. N is the number of years, which is 10. And FV is the face value of $1,000, also known as the future value in the equation. Now let's plug in our numbers. First, let's calculate the present value of the coupons. This comes out to $463.30. Next, the present value of the face value. This comes out to $613.91. Finally, we add them together. $463.30 plus $613.91 equals $1,077.21. As we predicted, the price is higher than the $1,000 face value. Using a financial calculator is much faster. I'll use inputs common to most financial calculators. First, always clear any previous work to avoid errors. Here are the inputs for the time value of money keys. Enter 10 and press the N key for 10 years. Enter 5 and press the I/YR key for the 5% market rate. Enter 60 and press the PMT key for the $60 annual coupon payment. Enter 1000 and press the FV key for the $1,000 face value. Now, all you have to do is press the PV button to compute the present value. The calculator will display negative $1,077.22. The result is negative because it follows a cash flow convention. In other words, you need to invest the money today or have a cash outflow in order to have a right to the future positive interest payments and payment of the face value of the bond. If the payments you receive are positive, the price you pay for the bond is a negative cash flow. So the price is $1,077.22. Google Sheets makes this calculation incredibly simple with its built-in PV function. First, click on any empty cell. Then, type the formula. It starts with an equals sign, followed by PV, then an open parenthesis. Inside the parenthesis, you input your rate, comma, number of periods, comma, your payment, comma, your face value or future value, and then type a closing parenthesis. Note that these are the same inputs as the financial calculator. However, we now are just inputting them into a spreadsheet format. Please carefully follow the syntax of the formula. If you miss the equal sign or command, for instance, you will get an error. Also, even if the syntax says you can input end or beginning, this is an optional field, so you do not need to enter it. Let's fill in the exact arguments for our problem so you can see exactly how to do this in Google Sheets, which will be similar to Excel. For the rate, we use the market interest rate, which is 0.05. For the number of periods, we use the bond duration, or 10 years. We will just input the number 10. For the payment amount, we use the annual coupon payment, or $60. So we will use the number 60. And for the future value, we use the bond's face value, or $1,000. So we will use the number 1,000. Note, these all are positive numbers, as these are cash flows we are expecting to receive in exchange for our initial investment. The initial investment is what we are valuing, or the present value of this calculation. So your final formula will look like this: equals PV, open parenthesis, 0.05, comma, 10, comma, 60, comma, 1,000, close parenthesis. When you press enter, Google Sheets will return negative $1,077.22. Just like the financial calculator, it shows a negative value to represent a cash outflow. Now here's something cool. If we set up the Google Sheets to have fields similar to each of the fields in the financial calculator, you can use the referencing of those fields within the formula to build your own financial calculator within your spreadsheet. You can see here that I have done this, and you can also see the formula I use to build out this referencing. If you'd like a copy of this Google Sheet for your own referencing, just leave a comment below, and I'll share it. I'll also include the formulas and sheets to the rest of the problem sets within this video. And there you have it. 3 different methods, all leading to approximately the same price for the bond, about $1,077.22. Now let's move on to problem 2. We're going to stick with bonds, but introduce a very common real-world feature, semi-annual coupon payments. You can see the problem on the screen now, and I'll read it out. A bond with a face value of $1,000 has a coupon rate of 8% paid semi-annually. The bond matures in 7 years, and the market interest rate is 10%. What is the price of the bond? The key difference here is the phrase paid semi-annually. This means the bondholder receives 2 smaller coupon payments each year instead of 1 big one. This changes how we set up our calculation, and it's a critical concept to master. Because payments are made every 6 months, we have to adjust our inputs to a semi-annual basis. Everything must be consistent. Here are the key variables adjusted for semi-annual periods. The face value, or FV, stays the same at $1,000. The number of periods, or N, is no longer just the years. It's 7 years times 2 payments per year, which gives us 14 total periods. The coupon payment, or PMT, is also adjusted. The 8% annual rate is split in 2. The payment is $1,000 times 8% divided by 2, which equals $40 per period. The market interest rate, or I/Y, must also be a periodic rate. The 10% annual rate is divided by 2, giving us 5% per period. An important tip. Let's check our intuition. The bond's annual coupon rate is 8%, but the current market demands a 10% return. Since this bond pays less than the market rate, it is less attractive. Therefore, we should expect its price to be lower than its $1,000 face value. It will sell at a discount. Now for the algebraic formula. The formula itself doesn't change, but we must use our adjusted semi-annual inputs. We are still calculating the present value of the annuity of coupons plus the present value of the lump sum face value. Just to remind you, the formula is expressed as C, the coupon payment, times the present value factor, plus FV, the face value, discounted back to today. For this equation, C is the semi-annual coupon payment of $40. R is the semi-annual market interest rate, which is 5% or 0.05. N is the total number of semi-annual periods, which is 14. FV is the face value of $1,000. When we plug in those numbers, we calculate the present value of the 14 coupon payments and the present value of the face value. First, the present value of the coupons comes out to $395.95. Next, the present value of the face value comes out to $505.07. Finally, we add them together. $395.95 plus $505.06 equals $901.01. As we predicted, the price is lower than the $1,000 face value, so the bond sells at a discount. Using a financial calculator is much faster, especially with these adjustments. Remember to always clear your previous work first. Here are the inputs for the time value of money keys using our semi-annual values. Enter 14 and press the N key for the 14 semi-annual periods. Enter 5 and press the I/YR key for the 5% semi-annual market rate. Enter 40 and press the PMT key for the $40 semi-annual coupon payment. Enter 1,000 and press the FV key for the $1,000 face value. Now press the PV button to compute the present value. The calculator will display negative $901.01. Again, the result is negative because it represents the cash outflow required to purchase the bond and receive the future positive payments. So the price is $901.01. All right, now let's solve this using Google Sheets. This section is designed to be a self-contained guide even if you jumped right to it. We'll use the built-in present value function, which you type as equals PV. This function calculates an investment's current worth based on its future cash flows. To use it, we need to provide the correct arguments, which must all be on a consistent semi-annual basis. Let's review the inputs for our problem. The function syntax is on the screen and the same as the first problem. Rate. This is the market interest rate per period. The annual rate is 10%. But since payments are semi-annual, we divide by 2. So our rate is 5%, which we enter as 0.05. Ampere. This is the total number of payment periods. The bond matures in 7 years with 2 payments per year, so we have a total of 14 periods. We enter 14. PMT. This is the payment made each period. The bond's annual 8% coupon on $1,000 is $80. We divide that by 2 for our semi-annual payment, which is 40. FE, this is the future value paid at maturity, which is the bond's face value of 1,000. Now let's put it all together in an empty cell. Your final formula will look exactly like this. When you press enter, Google Sheets returns negative $901.01. The negative result represents the price you pay today, a cash outflow in exchange for the future positive cash flows from the bond. And there you have it. All 3 methods confirm that the price of the bond is $901.01. Thank you for watching. If you found this helpful, please like and subscribe, and leave a comment on any other problems you'd like me to solve this way.